Hello and welcome back. In this video, I want to walk you through chapter 5 of the book R for Data Science, which covers data transformation. Now, depending on if you've read the PDF or the online version, you got a bit of a different chapter if you read it in advance. In the PDF, a lot of the things that are a bit more advanced have been deleted because I actually compiled the draft for the second edition, while on the website we still have the somewhat older first edition of the book. So, for example, one thing that was missing in the PDF is the section about logical operators and some of the more advanced things on missing values and comparisons. However, we will still cover this in this video, and I think it is actually not that important at this point. The reason why it isn't featured anymore in the second edition is probably because the authors have also decided that it is more important at this point that you get acquainted with the basics of data transformation before going into the somewhat more advanced stuff. Now, this said, let's get started. We start with the prerequisites and we copy the code chunk to a new R Markdown document, which I prepared, starting with a new code chunk, and we execute this. And I hope at this point you already know what this error message means. There is no package called NYC flights 13, so we go ahead and copy the package name, go to the packages tab over here, click install and paste it. And now the dataset gets installed as a package. That's all that the NYC flights 13 package does. It provides the dataset necessary for today's chapter. So once this is done, we try again to load the two packages. And as the book says, you should note the conflicts here. It is actually not that important, I think, because almost no one these days uses the filter command from the stats package or the lag command from the stats package, which is part of the base R installation that comes with R. So let's go ahead and close this. And first of all, we want to have a look at the dataset. So I make a new code chunk here and type in the name of the dataset, which is flights. And as we've discussed last time, this prints a nice overview of the dataset here. However, what I always prefer to do when I'm using RStudio is to look at the spreadsheet-like viewer, but as you can see here, our environment is still empty, and this is because this is a built-in dataset. It comes with the NYC flights 13 package, but it's actually not loaded into our environment, at least not visibly, because it is part of that package. So instead of hitting the little button, which usually appears up here, we can also specifically type in the view command. And this opens the same spreadsheet-like viewer. So we can see that we have 19 columns in total and over 336,000 entries. So entries means rows in this regard. So what we first want to do is have a closer look at what the individual columns mean. So we do this by either opening the help tab over here or by typing in the command question mark and then flights. I didn't mention this last time, but even though we are looking at the help file of a dataset now, it basically looks exactly the same to what I explained about help files on commands. So we have a title here, then we have a description, we have a usage, which is not really important here because it's basically just a dataset. So the usage is just the name of the dataset. And then we get the explanation for the different columns. So year, month, day is the date of the departure. Dep time and R time are departure time and arrival times. We see the scheduled departure time and scheduled arrival time. So we already know that there's often, or that a discrepancy is actually possible. So some planes leave later than they were expected to leave or they were scheduled to leave, and they also arrive later than they were scheduled to arrive. And then we actually have the departure and arrival delays here in minutes. We have the carrier, we have the flight number, we have the plane tail number, we have the origin, destination, airtime, distance, hour, minute, and so on. So if we have a look again, here we can see that this plane started on the 1st of January 2013. The departure time was 5:17, and if we look again in the help file, we can see that the format here is hour and minute. So this one actually means 5:17 a.m. If we scroll down a bit, we can check if this is in the 12-hour format or 24-hour format, and we can see it's the 24-hour format. So here we have 15:46, so 3:46 p.m. We can scroll a little bit to the right, and we can see here that the origin and destination are those 3-letter codes for the different airports. We also have the flight number here, and we should have the carrier somewhere. Yeah, that's here. UA, so probably this is United Airlines. Now, the topic of today's session and chapter 5 is data transformation, and data transformation means especially the dplyr package here. Dplyr is also part of the tidyverse, so we already loaded the package when we loaded the package tidyverse, and dplyr basically takes care of all the data transformation in R. We learn it because it is a lot easier than the base R installation or common alternatives which are around in R today. And as the chapter suggests, we are going to learn a few different commands here. And let me just copy those over. So I'm going to structure the session based on these commands. Here we go. So this is our agenda for today. And I will also, besides the book, use another resource, which are the fantastic comics by Alison Horst, which show these colorful little monsters that symbolize how the different dplyr commands work and also do a lot of other stuff. So if you're interested in learning R in a fun way, you can follow her on Twitter. She posts some of these comics every now and then. So the first function we are discussing is filter from dplyr. And the way filter works is that you have a data set, and then you only keep the rows that satisfy your condition. So inside of the function, you first have the data set, and then you have one or multiple conditions. So you can read this function as keeps rows from this data, so the data set which is called df, only if the type is otter and the site is bay. And it's important to note here the double equal sign. This is because usually the equal sign in R is reserved for arguments. So if you wrote this with a single equal sign, it would mean that the value for the argument type is otter. And this is not what we want here. We want a comparison, we want a condition. So based on this condition, we can have a look at the dataset here. So the data frame, which is called df up here, and we can see that it has 3 columns: type, food, and site. So when we check here, we only want to keep rows where the type is otter. So we can check and we can see, okay, only based on the first condition, we would keep the first row, the third row, and the fourth row. However, we also have the second condition, which needs to be true as well. And that one is that side needs to be bay. So the first and the third row meet this condition, and they also meet the first one. So what we're going to stick with is the first and the third row. And you can see the little monsters here doing the work. The first one which says which ones to keep, and the second monster which tells R which rows to drop. So let's put this new command into action. I'm making a new code chunk here. I'm using the filter command. Then I'm typing in the dataset which I want to use, which is flights. And then we can go into here, and the thing that the book does is it selects a specific date. So let's say we want to keep flights, I don't know, from the 7th of July. So what we do here is we want year to be 2013, and we want to be month was it 7 or 07? No, it was 7. And then the day is supposed to be 25. And as you can see, the number of rows is dramatically lower compared to the whole data set. It is 1,000 flights. These are the 1,000 flights that left New York City Airport. Was it New York City Airport? Oh, it was all of New York City's airports, so JFK, LGA, and EWR. So 1,003 flights left on this specific day. However, you will notice that our environment is still empty, and this is because we didn't actually copy the new element to anything. What we did instead was to simply print the new dataset or the filtered dataset to the screen, or in this case to our Markdown document. So let's go ahead and create a new object. We call this object Joule25. Use the assignment operator. So again, this is alt and then minus. And as you can see now, we finally have something in our environment. And we can again look at it using the view command, which is called when I click this little button here, and you can actually see it in the console down here. Now, let's say you also wanted to have all of the flights from the day after, and you might be inclined to write the new filter like this. But as you can see, this selects 0 variables because what we've actually done is to create a condition which is impossible to meet. And this is because the little and sign here and the comma actually mean exactly the same. So in this before, just to show an alternative, we could have also used commas. And the object which is created this way does exactly the same. If you wanted to include both of these days, instead of the AND operator, you would need the OR operator, which is this solid pipe character here. And if you're using a German or UK keyboard layout, you can make this character by pressing the button next to the left-hand shift together with the Alt character. If you have a US keyboard layout, you have to use the button underneath the backspace key. And when we now go ahead and run this, you can see that we managed to include both the 25th and the 26th of July. We can use these little arrows here to arrange the dataset, or at least arrange the view of the dataset. This doesn't actually change any of the data, it just changes in which order the data is displayed here. But as you can see, we have both the 26th and the 25th in this new object here. Instead of the equal sign, we could also use one of the other comparison operators. And as the book explains, we have the larger, smaller sign. Then we have the exclamation mark not equal, and the double equal sign means equal. So let's go ahead and play a bit with this. I'll leave it down here. And let's make a new code chunk. Again, we use filter. And let's say we only want departures which left after the 7th month, so after July. We would use this sign, which is the greater than sign, and we only want to keep rows where the value month is larger than 7. And here we go. We can use again the view command. Let's just call this df to get it into our environment. And as you can see here, we now have all the months that follow July. If we use the smaller than sign, we get the opposite, which is all the months before July. Here we go. We can also include July in this by using both the smaller sign and the equal sign. So here we go. Oh, that's the wrong one. So here we go. Now we have July included. Not equal. So the exclamation mark in R always negates the current comparison. So if we use that, we get all of the months except of July. Instead, we could also use the exclamation mark to negate the whole pattern. So if we say we have the month needs to be equal to 7, and then we negate the whole thing, we should get the same number of observations. So that is 307,000 something, and yeah, that's exactly the same here. So here we go. These are the different comparison operators, and we also learned some of the logical operators that are mentioned in the book, namely we know the AND operator now, the OR operator, and finally the NOT operator, which negates the current pattern. The only one left is the IN operator, which is a shorthand for comparisons between vectors that are longer than 1. And we can show this in a quick example. So let's say we have in our data set the months 12, 11, and 10. So the C means concatenate, and it creates a short vector. So it creates basically an object which only contains these 3 numbers. And let's say we use the equal operator here and ask it to say if this is equal to 12 or 11. So you might assume that what's happening here is that our checks if 12 and 11 are inside of here, but what actually happens is that you get a warning, and you should never take this lightly, because even though now you got the correct results, this is a bit random, and often it doesn't really work in that specific way. It might not do exactly what you wanted. So use the in operator instead. And once you do this, you know that the first 2 numbers here are actually contained in the second vector, and the third one isn't. So to translate this to a filter command, let's say you wanted to have the months which are in the short vector that contains 12, 10, and 5. So now here we go. We have this data set that contains 5, 10, and presumably 12. Yeah. And now the last thing the book mentions in this regard, and it's not actually specifically mentioned in the PDF, only in the online version, and I'm leaving a warning here, because comparisons with NA, which is missing, which is a missing value, are tricky. And so is apparently typing today. And let's go ahead and create a quick data frame using the Tibble command, same as in the book. And I'm creating 1 column in this data frame, which I fill with just a few nonsensical values. And in the middle of this, I place an NA character, which again means missing values. So when we look at this now, we can see it is a data frame with just 1 column and the values I put in here. If we now wanted to filter this, and let's say we want to keep only the rows with the missing values, you could think that this might work. But as you can see, what is returned isn't actually working, and RStudio helpfully displays the correct way to do this here, namely to use the function isNA and wrap this around x. So if we do this, we can now see that what is returned is a tibble, which is essentially a data frame with 1 column, unsurprisingly, and also 1 row, the row which contains the NA. And now I'll let you think for just 5 seconds what you would need to do to remove all of the rows which have an NA in the DF data frame. And I hope you remembered this operator here, the exclamation mark. So if we use this, then we get the 2 values which are not NA. And just because the book does that, let's add another comparison here with the comma. So we want it both to be true. We want the values to not be NA and to be, let's say, larger than 1. And then maybe one final note on the filter command. The conditions which can be placed after the name of the data frame that you want to filter basically need to be evaluated to true if you want to keep a line. So what does it mean specifically? Well, on the one hand, you could do something like this. You could write in true here. So then this is evaluated true for every row. Not very useful, but just to make this point. And then the other thing is that what we've done on top here. So we created a condition outside of the filter command and then checked which of the values are evaluated to true and which are evaluated to false. This is something that is really helpful when you're not super sure if your filter command worked in the correct sense, or if you want to chain a few different conditions and you're not sure if what you're doing is correct and you want to try it out on a smaller data set or a small object with some test data. And there we go. This is basically everything you need to know at this point about the filter command. Moving on to arrange, and there isn't actually a lot to say about arrange. It basically works like the little arrows that we have in the spreadsheet viewer here. And if we go ahead and arrange, for example, by distance, we get the flight with the smallest distance, which is 70 kilometers, I guess. Oh, minutes, which is 17 minutes. And then the longest flight, which is almost 5,000 minutes. But as I said before, this doesn't actually change the data set. What you need to do for that to happen is you need to use the arrange command, and we go ahead and say we create a new data frame called flights arranged. And here we use the arrange command. Then we have the flights data set, and then we simply put in the name of the column that we want to arrange by. So in this case, distance. Now, when we open this up and scroll over, we can see that this data set is now arranged by distance, and the smallest value is on top here. If instead we wanted to have the largest value on top here, we would have to additionally use the desc command for descending. And here we go. Now we have the largest value on top. One thing that we should note is that NA values will always be stored at the bottom. So if I go ahead and use this on my little toy data frame here, yeah, of course, it doesn't have this. It doesn't matter if I use descending or not. Both times NA will be at the bottom. Now, the two functions we talked about so far are filter and arrange, and those two really deal with rows of data. So filter selects rows which you want to keep, and arrange orders them in the way that you want. Moving on now, we deal with two more functions from the dplyr package, which are select and mutate. And those essentially select columns, which means it drops columns as well, or mutate, which adds new columns or overrides existing ones. Like arrange, select is rather simple. We basically have two things that we can do. We can either tell it which rows we want to keep from a data frame. So let's say we want to keep the year column, then it goes ahead and removes all of the columns which are not named year. We can do this with a couple different ones. So here we go. This way we can select the first three. What we could also do is look at this here and say, okay, what we really want to do is we want to select all of the columns from year to arrival time. We don't have to actually write all of the different column names. We can use the colon and say we want. So this then selects all of the columns between year and arrival time and drops the other ones. And then the second feature of select is that you can also drop columns. You do this by adding a minus in front of the name of the column. And if I go ahead now and do this, we basically retained all of the columns except of year. So note that you can't necessarily do both, because if I add month now here, because what select does now is to follow the first logic that it encounters here, which is to remove year and then keep all of the other ones, including month, which we've specified. We go ahead and do this the other way around. You can see that again it follows the first logic that it encounters, which is to retain year and remove the other ones, including the one that we explicitly specified. The book then also mentions a few helper functions, for example, starts with, ends with, contains, and so on. And really, those are important for you to remember when the time comes. And they can be a pretty big help if you have a couple of hundred columns, but it is unlikely that you will need them in this course. Just remember that there are helper functions that come with select and that you can use them. For example, the contains command, and say keep all of the columns that contain the characters EAR. And here we go, only year contains this specific succession of characters, so that's the only one we keep here. We can try this with something else. For example, arrival is abbreviated to ARR. So let's say we want all of the columns that deal with arrival in some way, then we can use contain, but you can also just spell out those three column names here, because what you actually get is a fourth one that you probably didn't want. And then a final note on select. If you go ahead and select columns in a different order from how they are placed in the data frame, so let's say we want day, month, and year, then R will order this in the correct way. However, sometimes you only want to reorder the columns and not necessarily drop any of them. In this case, there's a helpful closely related function which is called relocate, and here you can also spell out a different order, and as you can see here, it gets changed in the dataset while retaining all of the other columns. And then let's say you want to rename one of the columns without changing anything else about them. Then you can do so by writing the new name on the left-hand side of an equal sign, and then the old name of the column on the right side. And once we do this, you can see that the result is the same as before, and except that the column is now called days, and this works for relocate as well. And this is, I think, all that has to be said about select here. The next function we're talking about is called mutate. And this is probably the one that you will use most often in reality, because what it does is to add new columns based on existing ones. And as you can see here, the little monsters are hard at work. They are creating the new column called C. And down here you can see that the plan is to add column A to column B. And as you can see here, this works. In the first row, we have the value 1 in column A and the value 2 in column B, which added up is 3. We can test this inside of R by using the same data frame as before, which I created, the little toy data frame, which only has the column X. And we can make a new column called Y, which is based on X multiplied by 3. And as you can see here, it worked perfectly. However, most of the time, this is not what you want to do. What you rather want to do is base your new column off of a calculation between two old columns. And I'm going ahead and copying the example from the book in here. This is actually the example of the PDF version of the book, because it's a little more comprehensive than the version in the online book. And what you can see here is that we are creating two new columns. So first, again, we have the data set. Then we have the first new column, which is called gain. And then we have the second new column, which is called speed. And we talk about this last line here later. So let's get back to the data set. What is gain? So as you can see, it is departure delay minus arrival delay, which means it is basically the time a plane made up in the air. And when we look at the columns here, you can see that for the very first case, we have a departure delay of 2 minutes, and then we have an arrival delay of 11 minutes. So the first line should show 11 at 2 minus 11, which is of course minus 9. And then the speed is calculated by dividing the distance by the airtime. So let's check again what the distance is. The distance between airports in miles. So what we will get here is miles per minute, and of course this is not very commonly used. Instead you want miles per hour. So this is why you add the 60 down here. And then when we look at the help file for mutate, you can see that the dot before, so the dot in front of the argument, is simply there, so it's not mistaken as a new column. And what the before does is a little bit cryptic here, control where new columns should appear. The default is to add on the right hand side, so a new column in mutate would usually be added as the rightmost column. So it would go right to time hour here. And just to make this more readable, we add the before 1, which means on the very left before the first column. And when we run this now, we can see that the gain is as expected, -9, and then we have a speed of 370 miles per hour for this first flight here. Now, if this doesn't make too much sense for you because you've already become accustomed to the format of the data frame, which is to have the year, month, and day first, you could also play around with it a little. So we could use the after argument here and say we want to insert these two new columns after the day, which means to the right. And here we go. Now we have year, month, and day to the left, and then we have the new columns which we calculated, which is gain and speed. Now, just because this is also mentioned in the book, we also have the keep argument here, and as you can see, the options are to keep all, keep used, keep unused, and keep none. I personally really don't like this. I think if you want to change which columns are present in a data frame, you should you should really use the select command instead. And then the online version of the book mentions a few other things that you can do with mutate, or more specifically, variations of what we've already done. We have the lead and lag command here. Those are really useful if you need it, for example, to calculate how much time there is between departures. So let's say we wanted to calculate the pause at the airport or at all airports in New York City between the second flight here and the first flight. So what we would do is to take the departure time of the second flight and subtract the departure time of the first flight from it. So we now know that there are 16 minutes between the second row and the first row flight. And the way we would do this using lag is we want to make a new column called pause, and then we take the departure time and subtract the lagged value of departure time from it. So in this case, lag goes up one row. So we have this row, and then minus one row is 517. And then I forgot the comma here. And once I add the comma, we can see that the value for the second line is 16. Now, the value for the first line is NA, and this makes sense because you can't go further up than the first line. So this is basically the value of departure time minus an unknown value, which then again is an unknown value by itself. We also have cumulative rolling aggregates or cumulative sums. This is the one that I sometimes use. So let's say we wanted to know how much time planes that started at New York Airport, at one of the New York airports, spent in the air. So let's say we wanted to know this for the 1st of January. So what we could do is first we make a new data set, flights Jan 1st, then select, then filter flights, and then we only have the year 2013, so what we can do is to have only month which are equal to 1 and day which are equal to 1 as well. So there we go, a nice and small data set. And then we can use mutate on this new data frame, and we add all minutes, which is the cum sum of airtime. Oh, that was arrival time. I wondered, what's it called again? Yeah, airtime. And then we put this on the left again so that we can see it. And then here it took me a second to figure this out. I misplaced one of the closing brackets, and now it should work. So we know that the first flight here was in the air 227 minutes, and then the second one as well. So as you can see, this is nicely summed up over the day. And if we looked at this now, so you should always make a new object and not override old ones because it gets really confusing. But if we looked at this now and scrolled all the way to the bottom, we could see an NA. which is interesting. You can refer to the book to see that NAs are really contagious. If you have a missing value once, then you get missing values. But here up until line 471, it worked. And we can see that there were already over 80,000 minutes spent in the air by airplanes. And we are only halfway through the dataset here. Then we have the logical comparisons again. So if we scroll back to filter, we can borrow one of the comparisons from there. Let's say I wanted to make a new column which tells me if a flight started in July. Then I could do it like this. I just create a new column which is called July. We can again place this before. And as you can see, this is false in the first couple of lines. But if we say now we wanted to test if any of the rows indicate flights that started in the first month, so in January, you can see that these are true. So it really does the same thing as above, but instead of using the result from the comparison to filter the data set, we create a new column which stores the result, which is a logical vector. So logical means it can either be true or false. And then finally, we have this min rank function here. And let's just see what this does. So let's again write mutate one more time. We're using it on the flights data set. We just call this new column. And then let's say min rank of airtime. And again, we want to place this at the very left. So the new column tells us that out of 336 rows, the first row has the 267th, 674th shortest airtime. And this concludes the short introduction of mutate, but we will see this function many times over in this session and in the following sessions. Now, before I move on and discuss summarize and group by, I want to make two quick notes. The first one is that I wanted to highlight that the commands from the dplyr package are all worded as verbs. So this is why you sometimes see them referred to as the dplyr verbs. And I think this has been an excellent idea by the developers of the dplyr package, because it really tells you how a command works, what it does, and makes it really easy to remember. So the filter command, it's really easy to remember. It filters rows by a certain condition. The arrange command arranges your rows in a certain order. The select command selects certain columns. This is, I think, the only thing that is a bit hard to remember, that there's a difference between select and filter. Filter always works on rows, select works on columns. And then we have mutate, which transforms a new column or makes a new column by mutating old ones. And then the second thing that I wanted to note on is the pipe command, which is not directly from dplyr, but is one of the reasons why dplyr has become so successful. And the reason the pipe command is important is because it basically revolutionized the R language by adding a pipe command, which is also present in many other programming languages. And to show you the basic problem. Let's make a new R chunk here, and let's say we have our data set flights, and we want to filter this data set. Then we want to arrange the data set. We want to select certain columns, and then we want to make a new column. So how would you write this? Traditionally in R, you could simply put flights into the filter command. Let's say we wanted to get the months January, February, and July. And then if you wanted to arrange this data set directly, you would have to put this into the arrange command. So what would happen here is that R would first filter the data set and then arrange the output of the filter command. And let's say we want to arrange this by month, day, and departure time. Then let's say we want to select some of these columns. We want to take this a step further, and we actually only care about departure delay, carrier, departure time, and let's also add arrival time here. And then you can already see I also want to mutate this. Let's say we want to calculate the gain that we saw earlier. So we have the departure delay and we subtract the arrival delay to arrive at the gain, so the time a plane made up while it was in the air. Okay, here I actually forgot to select the correct column. I selected arrival time instead of arrival delay. And once we do this, you can see that it did everything we wanted. It first filtered the data set, then it arranged the data frame by month, day, and departure time. Then it selected a couple of columns. We saw that this is happening before because I accidentally removed the arrival time that we needed for our mutate comparison. So as you can see, this is quite tough to read, and the solution that some clever people who develop R packages came up with is to instead use a pipe. What does the pipe do? It basically takes the output from one command and pipes it into another one. So we can start by simply using our flights data set. And this is how it's usually done. This is a good practice. You could also write the flights data set directly into your first command. But usually what you do is you put the data set on top and then you make the first pipe character and you insert a pipe command by using Control, Shift, and M. And then we can again filter. And what I do here once is to make the piping process explicit. This is sometimes done when your data input isn't in first position. Some of the old R functions have it in the second or third position. But what the pipe command does is to insert whatever the result from the last line is as the first argument in the new function. So when we run this now, we can check this by just looking at how many rows there are in this new data frame, and we can see it is dramatically reduced from the original data set. It is plausible that we only have January, February, and June in here. We can also just remove the two. And as you can see here, this worked now. Let's add them back. So then what we would do next is add the pipe at the end again, make a new line, and then we can move on and arrange this. So this time I'm omitting the dot, so the dot is just a shorthand to insert whatever was the result of the last command before the pipe into a specific position, but by default this is inserted in the first position of the new command, so it's not actually important to have this here. It's completely common to omit this. So secondly, we want to arrange the data set. Then we wanted to select specific columns. So we selected these columns here. Can just copy this over from above. You can see here it currently has 19 columns. When we do this, it only has 5 columns left. And then finally, we wanted to use mutate to create this new column here called gain. And I hope you agree that this is a lot easier to read. We can read it as flights, then filter, then arrange, then select. So you can just pronounce the pipe as then, and together with the commands from the dplyr package, which are formulated as verbs, you can see that this works really well. It really shows, it is really easy to understand what this chain of commands does here. Now, just for completeness, there's also a third option, which is to run all of these commands individually. And we can do this to run all of these commands individually and put them into new data frames. So let's do this. Let's call the new data frame with the filtered flights df. And then I mentioned this before, but what you should never do is to use the same object twice to overwrite it, because if you mess up your order of commands, or I mean, you don't necessarily have to mess it up, just if you decided that one command should come before the other, you get some really confusing results. If you have a new object name for every object you create, then R will just complain and say object not found. But if you create a df and then overwritten it somewhere else and keep working with a new object called df, then you won't get an error message, you will just get very confusing results. So let's call this df2. And we want to arrange df. Then we want to select these columns from df2 now. And then finally mutate. And let's keep our naming convention here and call this df4. And then print this. So let's see, here we had 81,000 rows and 6 columns. And when we now run the different commands and make individual objects, you see we also have the same number of rows and columns. And there we go. In regular R, if you don't use the pipe command, there are basically 2 bad options of running multiple commands in a chain. The first bad option is to kind of write them into each other, and then the second bad option is to create individual objects for each of the different steps. The pipe command simply offers a better option to chain several commands and to transform one data frame in several steps. The only thing that the second bad option offers, which you might like, is that it creates these objects and you can look at the individual objects using the view command. So let's say you wanted to check if the select step really worked. So you could go ahead and say df3 and display df3 in the viewer. However, you can also simply do this in a chain of pipes by simply adding view at the end. And when I run this now, having the cursor in the view, it will run all of the commands above. The last command wouldn't run, it would give you an error because there isn't any data entered. But if I just run it when the cursor is here, I will get the spreadsheet viewer, and it has this dot as a name because this is what we actually entered into the viewer. It's the name of the object, and we can see it's the same as df3. So there you go. With this little trick, there's absolutely no reason to use any of the other two options. So then let's move on to summarize and group by. And these two commands really work best when they are used together. I will first quickly explain what summarize does. As the name suggests, it summarizes a data set into one value. Let's use the example from the book, or one of the examples. So let's say we want to calculate the mean delay of flights. The remove NA here is really because the mean command would display NA whenever there's even a single NA value in there. And this also makes sense because how can we calculate the mean if there are several flights of which we don't know the delay? So what this does is really remove the NAs before we calculate this. We could also make this more explicit using our new capabilities with the pipe command. So we could say we want to filter everything out that is NA in the departure delay. There you go. This would do the same thing. So we can also remove this argument here. And when we do this, it summarizes the entire delay column into a single value. So the average delay from all flights starting in New York City is 12.6 minutes. You don't necessarily have to use only one value to summarize it. You can also use different ones. So let's say we also wanted to create the median. But still, this data frame has only one row. And what we get here now is we have two different columns, each column showing just the one value that it summarized an entire column to. So this can of course be helpful if you start with a new data set and you want to get a quick overview. Usually the mean and median are really interesting. Another thing that we could do is to find out what the highest delay was. So we can use the max for maximum function. And then say we wanted to have the maximum delay. So there was apparently one flight which was 1,300 minutes late. But this summarize command becomes really, really powerful if we combine it with the group by command. And this was really what brought me over from base R to dplyr. I used base R for a couple of years before I realized how really powerful dplyr is. And the main reason for this was that I finally noticed the group by command, and this is just something that is extremely difficult to do without dplyr, and it makes it an amazingly powerful package. So what this basically does is to take one data set and split it up into groups. And instead of splitting up the data set manually into groups, which you could do by creating different objects, is you can simply say, I want to split my data set into groups by, for example, carrier. And we can run just this. You can run parts of a command if you select only the lines that you want to run. So when we do this, we get a data set which on the surface is absolutely identical to the flights data set minus the removed NA values here. But under the hood, the data set is now split into different groups. And by using summarize, we can make this visible, because what we will have now is one summary per carrier, so one summary per group. So we could check and see, for example, that the mean delay varies substantially between carriers. So for example, American Airlines here, or AS, I don't know what this stands for, only has an average of 5 minutes delay. And then when we go through it, we see that F9 has the highest average delay with 20 minutes, but the one we saw earlier, the really bad delay, I think this is the worst one, 1300 minutes. This was by the carrier HA. Now, I don't know anything about this airline, but my first impression would be that it has really a lot of different flights, and the mean delay is so low because usually this carrier is right on time, or when we look at the median, we can see the median is actually negative. So it seems that some of the flights are also ahead of schedule. But something that we could add here, which is really useful, is we could add another column called number of flights. And there is a special command in dplyr called n, which tells us how many rows are currently in the group. So we could use this without group by. We can add this to the command on top here, and it would tell us the whole number of rows in this data set. We remove the ones with NA in departure delay, so this is a bit lower than the entire data set, but it shows us how big this is. And when we do this here now, we can see that actually HA doesn't have too many flights. In 2013, when the dataset was created, it only has around 342. And then when we look at F9, for example, it has just a few more, but it is really dwarfed by, for example, the airline B9 here, which has over 50,000 flights in the dataset. And now that you know the most important dplyr functions, we can use them together to answer a quick question. So I'm wondering, why are some of these carriers doing so poorly? And maybe is it because some of them don't serve on long distance flights? So on long distance flights, there's simply more that can go wrong. There could be bad weather along the way, a crew member could be sick, and it's not possible to find a replacement quickly, or it is possible, but the replacement needs to pack a few things because they're going away for a couple of days with a long distance flight. So maybe, yeah, some of the carriers just do less distance, and this is why they have less delay. So let's go ahead and remove all rows where the distance is missing. And then we want to calculate the mean distance. And to make this even more interesting, we want to display this directly in a plot. So let's pipe this into ggplot. Usually I would now put in the data first, but since the data is provided by the pipe, we can simply leave it empty and can directly start with the aesthetics. I want to make a scatter plot, so I'm starting with the x-axis, and let's put the distance here. And then on the y-axis, I want to have the mean delay. And let's differentiate the carriers by color. So let's map the carrier to color. And then you have to watch out not to use the pipe command here. You have to use a plus to combine different layers in a ggplot. But let's do this here just for fun to see what happens. So I'm adding the geom point. And this is everything that we should do. And here we go. R immediately gives us the correct error message, which tells us, did you use the pipe instead of the plus? Yes, indeed, I did. So let's replace this. And let's look at this plot. We can see there are a lot of carriers. So ggplot almost ran out of colors. But what we can see here is there isn't really a big connection between distance and mean. We can see that even though some of the carriers have a really low mean distance, their delay mean is all over the place. This is basically what it looks like if you have no connection between two variables. Let's say we also want to look at number of flights. I hope you remember that there are a few more aesthetics that we can use. I want to use size here. So let's use size to just display the number of flights. I'm copying this over so I don't make another spelling mistake. And here again, I would say there's pretty much no connection between the number of flights and the delay time. We can see that down here, the one which does really good in terms of delay doesn't have that many flights, also doesn't do a lot of distance. And then when you compare it to this one, which also has very few flights, the delay mean is much, much higher. So what we know is that we need another hypothesis. There's something else which explains the delay here. It is probably to do with the quality of the airline and how much money they spend on the spots at the airport. So something else that explains why some of these carriers are doing rather poorly. So now that you know the basics of the group by and summarize command, we can go a little bit more into detail. So the first thing I want to highlight is that you can also group by several variables. So let's have a look again at the data set. We group this by carrier. What else could we do? We could group it by origin. So where did the plane start? And then when we run our summary command, here there are two things. So first of all, we have another new column here, which is origin. And now for every carrier, we see the different origins where did the flight start. And then we get a mean delay for this combination of variables. The second thing is that we get this message here. Summarize has grouped output by carrier. You can override using the groups command. And what R is doing here, or what the dplyr package is doing here, is to select a default value for you, because once you have multiple variables to group by, this groups argument here kicks into place. And as you can read at the bottom here, when groups is not specified, it is chosen based on the number of rows of the results. If all the results have one row, you get drop last, which means one of the groups is removed. And if the number of rows varies, you get keep, which is what currently happens. And this is why we get this message here. So once you have multiple variables to group by, I think it's a good idea to specify what you want to do with the grouping afterwards. And I usually want to keep the groups. So if we run this again, you can see that the message disappeared. And when I then want to run a different command without the groups, I use the ungroup command, which is basically the opposite of the group by command, and it completely removes the groups. We can test this by simply plugging it in here directly after the group by command. And when we do this, nothing happens because I left the pipe down here. And now it would be a little bit confusing. Let's see what happens if we try to run this again. We get error in flights because actually what happened was that the command didn't finish and R was kind of stuck here, but now that I remove the pipe, it should work. And you can see we have, as in the beginning when we didn't have any groups, we have just one row with the results for the entire data set. Okay, so let's put this at the end. It's usually a good idea that when you run a group by command, that you either specify to drop all of the groups afterwards or to ungroup explicitly, so that when you save this in a new object and then you later work with this object, you don't get some very strange results that you can't explain because you actually still have groups there. And then the second thing I wanted to highlight, and this is also mentioned in the book, is that group by also affects a couple of other commands. Specifically, the two commands which are affected are mutate and to some degree filter. So let's go with filter first. Let's say we use again the flights data set, and let's say we want to keep only the flight which has the largest delay. So let's go with departure delay. And to get the delay with the highest value, we can say we want to keep the row where the departure delay is the maximum departure delay. And we get a data frame with 0 rows. So apparently there is no flight where the departure delay is the same as the maximum departure delay. And the reason for this is because we still have NAs there. So the maximum departure delay evaluates to NA, and then we can't compare anything to NA. So let's use a filter first to get rid of the rows where departure delay is NA. And then here we go, we have a single flight. But where this comes in handy is when we have groups. So let's group by the carrier again. And when we use this now, we get the flight with the highest delay per carrier. Just for the sake of it, let's also use select in this pipe. So we only want carrier and then departure delay. And then here we go, we get a nice list. Or you know what, we can also throw in a range here. So we want to know which carriers have the highest delay. And then we have the list ordered. And then the second command, which is affected by groups, we just go with the same groups again here, is the mutate function. So let's say that instead of departure delay, what you want to express here is the percentage that one of the flights contributed to the delay of a carrier in total. So we make a new variable that is called departure delay in percentage. And then what we need to do is we divide the departure delay by the sum of all departure delays. And this is the part, so the sum is the part that is affected by the group. And to get this to a percentage value, we just multiply this with 100. And let's again select the two columns that we are interested in. But we don't need a range this time. So you can see the result here. NR is displaying the percentages in the scientific notation. So you have this E at the end and then -4. This means you have 4 leading zeros before you get to the actual value. So that means we have 0.00028% that this specific flight makes up here. You can turn this off. You can turn the scientific notation basically off with the command option scipen 999. This just sets the penalty really high, and R is not turning to the scientific notation until it is really, really, really necessary. That needs to say options. And then when we run this again, you get it displayed in a normal notation. Depending on how used you are to the scientific notation, it might make sense to turn this off. But here we go. You can see that now the departure delay is expressed in percentages, and this is different for every carrier. So here, for example, we have 2 minutes departure delay, and here as well, but the percentages are really different, probably because the number of flights for this carrier is different from this one, so one departure delay has a much smaller weight here. So this concludes the group by function, and really all we wanted to know of the main dplyr verbs, but the book also mentions a short case study, which we can also do. So the book mentions the idea that maybe individual airplanes affect the arrival delay to a large degree. So as you can see here in the tail number, this is basically the name of one specific airplane, and we can calculate the mean arrival delay for each specific airplane. So let's go ahead and do this. We take the flights dataset again. Then we first remove all the flights that have an NA value in the column we want to look at, which is arrival delay. we group by the airplane, so we group by the variable tail number. And then we can summarize the delay by calculating the mean delay. And then, as before, let's look at this using the view command. So this way I can just sort it visually. We can see that there's one plane which seems to be always very early. It has a mean delay of negative 53 minutes. So it's on average 53 minutes ahead of schedule. And then when we look at the other end, we have one airplane which seems to be on average 320 minutes late. We can also go ahead and look at this in a plot. We can use ggplot, and again, we don't have to type in the name of the data frame here because it is directly piped into the ggplot command. We map the average delay to the X aesthetic, and then we can use a new geom, which is the geom_frag_plot. And again, I made the same mistake, this time not on purpose. We have to use the plus here, of course. And now we finally get the plot, and we can see that most of the airplanes have an average delay close to 0, and then we have a long tail of airplanes which have a really high average delay. The reason why the book is mentioning this becomes clear when we include a second plot. We start with the same lines, but then in our summary, we also want to have the number of flights that each airplane makes. And when we plot this now, we can use the number of flights on the x-axis, and on the y-axis we want the mean delay. And if we use this in a scatter plot, you first don't see a lot. We can reduce the alpha value here, let's say to 0.1. And when we look at this now, we can see that the extreme values, so the airplanes which have a really, really high mean delay or a really low mean delay, only ever show up in the data set once or maybe twice. And then the more flights a plane made in the data set, the closer it is to an average of a 0 minutes delay or a very small delay. So we can see we have one airplane here which made almost 500 flights in the data set, and it is really close to a 0 minute delay on average. And then usually you're more concerned with general trends instead of these very extreme outliers here. So what we could do to zoom in is we could filter and only keep the airplanes which have flown at least 25 times in our data set. And what this does is to reveal that there's actually not that big of a trend. No matter how often we see an airplane fly, we have a bit of a cluster here around the 0 delay, but then they're basically all over the place. Some of the ones that fly over 200 times have a rather high delay mean, and some have a rather low delay mean. And what we can also see is that all of the airplanes which have flown less than 25 times are removed here, and we have a bit of a gap between the x value 0 and where the actual scatter plot starts. And with that, I leave you for today. This concludes our session. There is a second case study in the book that you can maybe work through as a homework. I also left the exercises in here, so please work through them. Again, the second case study is only present in the PDF version, which has a little bit of a different structure of the book. So thank you and see you in the next session.